Okay, so like I said before, up on Canvas, there's a module that says obviously lecture notes and their PDF files, pretty much all the slides up there. So we're going to start here with chapter 12, which is about chemical equilibrium. And like I said, that is pretty much the main topic of the season here, which is chemical equilibrium. As I mentioned earlier, not joking. Pretty much we will talk about every equilibrium you probably never wanted to know about in this particular class. Now, when we talk about chemical equilibrium, it does involve a certain type of reaction. And if we have a reaction such as this here, A plus B goes to C plus D, A and B are our reactants, right? Yes. And C and D are our products, right? So we have our reactants, we have our products. And in this type of reaction, this is a reversible reaction. And you might remember a reversible reaction or sort of coming into contact with that by seeing these two arrows that head in both directions. You most likely came across that when you talked about electrolytes, maybe some weak electrolytes, where things basically stay together and they do not break apart into ions. Things like weak acids and weak bases are weak electrolytes, and we deal with a lot of those in this particular class. Now, what those arrows represent is there's really two directions this reaction can take place. So unlike a single arrow reaction where it's kind of like a one-way street where the reactants just drop off to the products, in a reversible reaction, we have two arrows that head in opposite directions. And we have in the forward direction, going from reactants to products, that is what is referred to as the forward direction. So this reaction can proceed from left to right. Our reactants can come together to make our products. And at some point when this reaction starts or begins and continues, there will be a buildup of products. And those products will then be able to come back together and actually head back the other way and make more reactants. And the reaction can then head in the opposite direction, going from products back to reactants. And that is what is known as the reverse direction. So this type of reaction, which is mainly what we deal with here with equilibrium, are these reversible reactions where eventually we have really stuff flowing in both directions. We have reactants going to products, products coming back to reactants. This will continue until what is reached is equilibrium. And this process will continue until equilibrium is reached. So let's talk about really the first sort of misconception about equilibrium that students have, which is the word equilibrium and what it means. When a reaction reaches equilibrium, sometimes people think equal is in the name equilibrium. So it means, hey, I must have equal amounts on both sides of the arrow. And that is actually not what equilibrium means. So when a reaction reaches chemical equilibrium, what it's actually referring to is kinetics and the rate of a reaction, which most of you probably covered like one day in 200A, I imagine, at the very end of the semester. I know I did too. It's all right. It happens. But what we're talking about is the rate here. So when we say equilibrium is reached, what it actually means is the rate of that forward direction of this reaction will essentially equal the rate of the reverse direction. And that is what is meant by chemical equilibrium. It means just as quick as it goes from reactants to products, those products will recombine and make more reactants. Now, what does that mean? Does that mean you end up with an equal amount of everybody on both sides? The answer is usually no, it doesn't mean that. It means that when this reaction actually reaches equilibrium, what it actually does is it locks everybody into place. and it locks everybody into place in terms of their concentrations they're at that point, or if you're dealing with gases, their pressures at that particular point. So what that means is I can do it here maybe we have this reaction initially, we take this reaction, and maybe we started with 4 molar of this guy, and maybe we had like 2 molar of this guy, and we had 0 of these guys, so nothing really going on there on the product side. This reaction starts. By the way, if I had this situation, what is the only direction this reaction could go? It could only go in the forward direction, right? Because we have no products to go in the reverse direction. So if you were in this situation, you know for sure that the initial part of this reaction should pretty much be all reactants going to products, right? It's kind of almost like a one-way street at this point. And what we would see is probably, right, the amount of reactants start to decrease, right? Because the only way you can make products is to use up some reactants. And we would actually start to see the amount of products start to increase, right? So we'll start to see some products formed and stuff like that. As this reaction proceeds and we start making those products, we will eventually kick off the reverse reaction, heading backwards from the products back to the reactants. And now we reach perhaps equilibrium. And what it means when it reaches equilibrium is maybe we end up with 3 molar of this guy, 1 molar of this guy, maybe 2 molar of this guy. I don't know, maybe like, we'll do 3 molar of that guy, right? Now, when we reach equilibrium, and if this reaction hits this equilibrium point, what it means is it will lock into place those concentrations. A, B, C, and D at this point, in this made-up example, will continuously have those concentrations, as long as you don't do anything to screw up the equilibrium, which we'll talk about later in this chapter. But if you leave it alone, because just as quick as it goes to the products, it comes back to the reactants, there's really a net no change happening in the concentration. So everybody just gets locked into place. And even though it's kind of going back and forth, it pretty much stays at the same spot all the way through. As you can see, it doesn't mean we got the same amount on both sides or anything like that, or the same amount of everybody. So one of the first misconceptions about equilibrium is it means everybody just gets equal on both sides. But it again is really referring to that rate of the forward direction and also that reverse direction. Any questions on that there? Now, chemical equilibrium, as I mentioned, is the state where all of our reactants and products concentrations do remain constant once it reaches equilibrium. Now, one of the weird things about sort of a reaction that has reached equilibrium is, for example, let's say I mixed a whole bunch of stuff into my wonderfully drawn beaker here. And it turned the reaction red, and it was all kind of colorless, maybe a little yellow solutions. But you throw them all together, this reaction reaches equilibrium, and now it turns red. And to you, when you're looking at the beaker, you go, oh, the reaction must be over. It kind of turned red. That was kind of like maybe what I was waiting for. Nothing much is happening. It just looks like a beaker of red solution. So on the kind of macroscopic level, when you look at a reaction that's equilibrium, it may look like nothing's happening. It may look like it's over. As it mentions there, it may look like it's static. But if you were to sort of super zoom into the beaker, and let's just say this was the reaction that turned it red, if you looked into the beaker, what you would find is you would have a lot of A and B going to make C and D, and you would then have a lot of C and D going backwards to make A and B. So there's just a lot of this activity that's constantly going on the molecular level that you can't see with your naked eye. It just looks to you like not much is going on in there. It's kind of turned red and it's staying red. So there's a lot of activity that actually happens to keep it at that state. So equilibrium reactions are very interesting reactions in that sense that it can look like it's over, but there is still a lot of activity happening. Equilibrium reactions, as we will talk about, are interesting reactions in the sense that you could do something to an equilibrium reaction. So I could do something to this reaction and turn it from maybe red to, I'll go with blue since I don't got limited color choice. I could actually do something to this reaction and then it could go from red now to blue because I did something to it. And they're such good reactions that you could change your mind and go, I kind of like red better in terms of the color. You could actually do something to that reaction and make it go back to red. And you can make it go back to blue. You can make it go in between those two colors as well, depending on what you're doing. So these type of reactions are sort of always working reactions. They're always reactions that can constantly be changed a little bit. But one of the things that's also really interesting about equilibrium reactions is if you have a system that's at equilibrium and you do something to it that screws up the equilibrium, the reaction itself will want to self-correct itself and get itself back to that equilibrium state. So you could do something to this reaction, it will completely screw up the equilibrium, but what the reaction is able to do is go, uh-oh, this is not good. I like have too many reactants. I need to start making some products. And it's able to by itself go, okay, we're now going to send some things to the product side and get itself back to a state where the forward reaction and the rate of the reverse reaction will once again equal each other. Now, that may look different to your eye when you're looking at it, like my example here. When I do something to that red beaker and screw up the equilibrium, it's going to adjust the reaction. And when it returns to equilibrium, which is that state of the forward reaction and reverse reaction equal each other, it's actually going to look more blue than it did before. And the blue beaker is actually at equilibrium as well. And then, like I said before, I could do something to a blue beaker. It will mess itself up. It will come back to equilibrium on the red looking. So there are very interesting reactions in that sense. They're almost, you could think about it as being like self-correcting type reactions that their ultimate goal is, no matter kind of what you do to it, their ultimate goal is to reach that equilibrium state. And even if you screw it up, it's going to try to get there and get to that state where the rates are equal to each other of the forward and reverse direction. And as we'll talk about later in that chapter, that may require that reaction to make more products to do that. It may require more reactants to be made to do that. And there's a lot of factors can affect kind of which way it has to go in terms to reach that equilibrium state. Any questions on that?